Before we move to learn the spray combustions, we need to give you some understanding what kinds of spray burning we may have for different spray combustion systems. Since you have a different combustion spray combustion systems in various operation circumstances, you may have a different kinds of spray combustion characteristics. And before we learn the detailed combustion frames, spray frames, you need to know the systems you may have for practical applications. Now we move to our page 3.15, and we talk about we introduce some spray combustion system, and those materials taken from the Facebook in 1977. Actually, he has a new version, but unfortunately, Professor Fest already passed away several years ago, maybe even earlier. I forget the exact time, but he's the very famous guys on combustions. Now, let's look at several applications to let you know how to analyze the spray frame behavior. The first example here, the first example that tell you the application basically is a so-called pre-vaporization system. Pre-vaporizing system, that means that you use a spray, liquid spray, but before combustions, let all the liquids be gasified, okay, pre-vaporize. That means that when you move to the combustion region, actually you do not have a spray, you do not have a droplet. Basically, they just give you, they will provide a few vapor and mix with air, oxygen in the air, and then they go through the combustion process. In this sense, actually, for the spray itself, it's a non-burning spray. Okay, burning happen in the gas phase. Okay, and a typical example for pre-vaporization systems, for example, later on I will show you a more precise pictures to let you to learn the so-called afterburners for air fighter or aircraft. And the lean combustor carburetor typically used for the automobile, right? For your, but this is a carburetor actually is already phased out. Not too many carburetor car still still in the market, right? Carburetor basically people understand those kinds of mixing of gasoline and air occurs before the spray moving into your combustor in the engines. The mixed well means that they will have a very efficient gasification of your gasoline, and the vapor will mix well with the air. Then they will be sucked into your cylinder to be finish the combustion process. Therefore, you can see there is a spray mixings in front before the combustion process, right? Then that means that we are dealing with the non-burning spray atomization structures, okay? And the other one is the so-called ramjet. Later on, I will give you some example. And the configuration, you can imagine something like this. Actually, those kinds of application operates continuously. Therefore, you can study the problem. Basically, you can see it's a steady, and in many cases, the combustor is asymmetric, and you can try to simulate as a one-dimensional flow is okay, and you still can have a better understanding on it. For this case, you can try for the coordinate system. You just need to consider the variation of your droplet atomization along the actual distance. And this is the typical analyze on the problem you may have, and how can you study the spread. And for this case, actually tell you the spread basically they were under atomization and a gasification process. The combustion will be further in the downstream sites, and it can be separate study as based on the gas phase combustion. And for all the flow field, you can treat as a steady and a one-dimensional flow. Okay. For the second one, we are dealing with liquid fuel rocket engines. Liquid fuel rocket engines. Usually, for a rocket engine, you need to think about the main purpose for the spray combustion for the rocket engines. For the rocket engines, usually the combustion chamber has a small length. That means that you need to finish the atomization, gasification, mixing in a short distance. Therefore, the design for those kinds of efficient atomization through the mixing and burning, then you need to think about you can distribute the supply of the liquid fuel and the liquid oxidizers in many injectors and try to then mix very well in a short distance. Okay, this is the typical part configuration for the liquid rocket engines. You can see there is a two line. One line may be the fuel, the other line corresponding to liquid oxides, and they will have later on I will give you some example to tell you there were some arrangement for your injectors, and those array of injectors have the arrangement to promote efficient atomization and mixings, and later on you will have a well mix together. Then you go to the spray burning. In this case, you will figure out, since the liquid rocket engines still can operate continuously, you can treat your problem as a steady. Okay, and the combustion chamber is compact, and they will move along the actual direction very relatively uniformly along all the cross sections. Then you can treat it as a one-dimensional flow. But in this case, the burning of your spray, okay, you may have a spray atomization in front of the injectors, but later on, because they have a good mixing with air, then they will, the good mixing with the oxidizer and the fuel, and they will start to have a burning. And in this case, there's still certain amount of droplet exist and mixed with oxygen. And here you may see the spray frame has a certain characteristic of a so-called premix frame. Okay, and for these kinds of spray combustion, actually they can control both of the diffusion burning from the droplet and also the premix type. Okay, later on we will have a certain discussion on this. Now the third one is the more general applications for gas turbine combustor. Okay, for this case, usually we use this as for the gas for the aircraft. You will suck the air coming from the outer surrounding into your gas turbine combustor, and the flow will separate as two streams. One stream is a head just move into the combustion chamber. We call this as a primary air, and the secondary air will flow to the anus of your combustor, and later on they will flow into a different downstream area. Actually, those kinds of secondary air work as the cooling fluid to quench the heat absorbed by the liner of your combustor, because the gas turbine actually is is attached to the aircraft. Okay, usually for in the combustion chamber, you need to take away from the heat absorption of your combustion chamber. For example, for diesel and gasoline, they are very hot inside of your cylinder, and those heats will be absorbed by the cylinder wall, and you need to take those kinds of heat away. Otherwise, the material will be failure. Failure occurs on the material because the temperature is too high. For the car, you can carry some water, right, to cool it down. But for the gas turbine, we use the air coming from the outer environment. The air is cool. The secondary air is cold, and they can carry certain heat out. But those air coming from the combustor in front of the combustor. They spend they use some work on it. Then this is the value energy you may have from the secondary air. Then still you need to, because they have oxygen, and then you can throw it into the combustion chamber to finish the final process of your burning, to make all the burning be complete. Okay. In this case, the spray impinge along the center line. Okay, spray is separate with the primary air coming from the outer strings, and they will tell you the basic combustion structures. Fuel separate with separate from the oxygens. Then the flame characteristics basically controlled by overall steady diffusion flame. Okay. Now, the previous combustion type for spray, basically they will involve a certain degree of premixing for liquid rocket engine. Okay, but for gas turbine combustor, usually we study it based on the spray diffusion flame. And in this case, you still can treat it as a one-dimensional flow. Now we move to the industrial furnace. Industrial furnace has the fuel supply and the oxygen supply basically very similar to the gas turbine combustor, but except the combustion chamber for the industrial furnace is much larger than the gas turbine combustor, which means when you have a large combustion chambers, now the influence coming from the gravity, the natural convection, become very important, since for the industrial furnace, the burning region is very large. When you have a large burning region, in this region, temperature is high compared with the low temperature environment. This temperature difference will enhance the density difference. Okay, and the density difference will give you a very strong buoyancy effect. That means that you cannot treat your flame is symmetric. For example, for gas turbine combustor, you can see you have a diffusion burning very nicely because the flame is short. But if you have a large flame, a longer flame, and the buoyancy effect that come in, they will change your flame shape. Okay. Then we extend to consider the one-dimensional spray diffusion flame for the gas turbine combustor. To think about those flames in industrial furnace, then simply you still you can treat it as a steady and a diffusion flame, but you need to consider the three-dimensional characteristic for this distort diffusion flame. Okay. If you go through from the top one, basically the differences is that are here. The first one, basically, we are dealing with spray atomization. Combustion is not related to the droplet exist. Okay. The second one, they will give you the spray burning has a certain degree of a premixing. But the third one, they tell you there is a purely fuel separate from the oxygen. Then the spray burning will be diffusional, and you can simulate it because this is a combustion length is small. Then the flame behavior you can treat is one-dimensional. But for the real application for the large size of combustion chamber in the industrial furnace, you need to study it as a three-dimensional spray diffusion flame. The previous four examples, actually the burning is continuously operates. That means that you can study those kinds of burning process are steady. The exception one for our application is the diesel engine. You need to think about the time variation. That means that burning basically is a transient characteristics. As you remember, for the diesel engines, the process for the burning, actually you try to suck the air into your cylinders, and you push those kinds of air and to increase their pressure to a certain high pressure status. Then you inject your diesel spray into this high pressure. Since when you when you increase the pressure of the air, then the temperature is also increased inside of the cylinder. Even you have the air only, but the pressure is high, temperature is high, then you inject diesel fuel into this high pressure, high temperature air environment. Since the temperature is high enough, they will have an auto ignition occurs. When you inject diesel spray in, then they start to burning continuously along with the time variation. Okay. Then here they tell you the spray burning in this sense they were transient, and there are several things occurs simultaneously in the process of burning. For example, when you have a diesel spray injecting into this high temperature region, then you will figure out the spray coming out. They will experience the first step is the atomization, right? And they will produce the tiny droplet, and a tiny droplet has a chance to meet with the air inside of your cylinder, and they try to have a mixing. And when the mixing, the process complete to give you a suitable concentration for ignitions, then ignition occur. Flame will exist in the process, and those flame will will enhance the burning later on, and finish all the droplets coming out and complete the combustion process, which means in this process, consider the burning of diesel sprays. Actually, you need to understand this is a transient, and basically they are diffusional, all right, because the spray initially separate with oxygen. But usually you need to remember when you define a premise flame or diffusion flame, usually based on the initial conditions. But in real combustion field, especially in the downstream of the different kinds of combustion field, you always feel there is a certain degree of permission occur. Okay, you cannot have a very distinct boundary for diffusion burning or premise burning. Okay. And here they mentioned the ignition catalysis is very important for diesel spray combustions. And for this case, the spray burning actually not only depends on the three-dimensional coordinates, then they will change with the time. Okay, that means the analysis on the diesel engine combustions, you need to think about the more complicated flow structure you may treat it. Okay, and I try to give you some understanding on the differences for the spray burning in different applications. Okay. Now I give you some example to let you know how to do the simulation. For example, this is a typical one for gas turbine engines, and this is a layout for a common gas turbine engine. As you mentioned, there is in front of a combustor, there is a diffuser, and they also have a compressor ahead of a diffuser, and they will push the air coming in to the combustion chamber as two streams. The center stream basically is a primary stream. They will go accompanied with the fuel node, the liquid fuel from the nozzle, and then the mixed oil or come up as a combustion in this combustion region. But the secondary air will move around the combustor anneals. Okay, and there is some liner opening. They will allow those kinds of cool air flow into your combustion chamber, and those cool air, the secondary air, basically they can cool down, and they will absorb certain heat from the liner and to protect the materials of your combustion chamber, the surface. Okay, and in this case, you can think about the spray operation. Injections is continuously supply for the burning. Then, if you try to analyze these programs, now think about it. There is give you the example. You can see since we mentioned there is the one-dimensional flow, right? One dimension along the axis of symmetry. This is a variation along the, for example, is a z-axis. but you can study is cylindrical coordinates. Okay, now fuel injecting out from the center, air coming from the surrounding, and they will produce a so-called diffusion burning. Okay, this since the design for the gas turbine combustor, the flow behavior actually they will provide certain recirculation zone here near the corner of the combustion chamber. And since they have some entrainment air coming in, the secondary air coming in, they will produce some mixing in the downstream to push your hot products flowing back and to enhance recirculation and also mixing in this region. Those kinds of recirculation mechanism somehow is useful to redistribute the thermal energy in a large region, then they will reduce the temperature lower than the threshold temperature for thermal NOx formation. We call this as a so-called low NOx burner mechanisms. I will show you later. But here you can think about those kinds of descriptions based on this geometry can be probably to be simulate the real combustion process in gas turbine. Okay, and here they tell you there's some droplet size distributions burning occur in these regions, and when they finish the gasification, burning, mixing and burning, then those kinds of emission hot products will move to the downstream side, and those exhausts the hot products and later on to push the gas turbine to operate. Okay, this is the combustion process for the gas turbine. And for the industries, the furnace, let me change the slides. Okay, I give you a typical example for the burning in boiler. Actually, this is another good example for spray combustion. Basically, I took these figures actually burning for the turbulence codes. But actually, you can figure out that the frame structure is very similar for the spray frame compared with those kinds of burning of the turbulence code. Okay. Here, the left-hand side represent the pulverized coal systems. Okay, they will crush the coal into the very tiny coal particles, and those coal particles were pushed by the air, and they will blow into the interior of your boiler, and they have a different nozzles to impinge out the coal particles to burn with air. Then you can see there is a flame exist. And this flame basically tell you this is a three-dimensional flame shape, okay? And typically this is a spray diffusion flame, or I'm sorry, I should say the pulverized coal diffusion flame. Yeah, but if you have a spray diffusion flame, it's very similar like this. And from the hand side to the right hand side, actually they try to change the angle of your injection nozzles, because when you change the nozzle, you will change the flame shape, and the flame shape change, then you will change the major heat release region to up and down. For example, the left-hand side tell you the major heat release region is almost in the center part of your boiler, but later you can see the flame shape is more horizontally injecting out. That means the hot regions reduce, decrease to the lower portions. And the right hand side, actually, the injection of your coal particle actually has a angle point to the downstream to the lower portion. Then the whole hot region will move more to the lower portion. by this kind of change the angle of your injector, that you can change the loading of your furnace. Okay, but I just want to tell you this is a typical frame shape for the pulverized coal frames. And actually, for the spray cone, if you burn the heavy oil in a boil, you still can have this kinds of frame shape. Okay, they tell you this is a three-dimensional spray frames, but it is steady since all the boil operation are continuously uh, are continuous. Okay, now we go back to tell you some formulations for furnace, and to tell you, give you an example. For example, this is an incinerator. The structures for incinerator is very similar for the industrial furnace. Okay, here the incinerator, they will give you some solid filling because you hope those kinds of solid materials, or for example, there is the waste, and you want to provide a certain heat to that those kinds of materials to have a thermal pyrolysis. Actually, you will provide a stable spray frame, okay, and a steady burning. But in this case, the solid field will solid materials will fit continuous, and they will exist. In this case, they will more accumulate closer to the surface of your whole incinerators. But usually for the mixing, for the good heat transfer, you need to make a good mixings by turning the incinerators. Actually, they tell you, if you look at the cross section, actually all the combustion chamber is rotating. Okay, and the thermal radiation coming from the flame will transfer heat to your solid material, and they still have some heat will followed by convection, and some heat followed by conduction out. But when you look at the thermal pyrolysis for the solid materials, you will find out initially they have a driving thermal decomposition because they will absorb heat. At the first stage, they will release some low boiling point volatile or water coming out. Then they will start to have some ignition of the evaporate vapors. Then finally, they just remain some solid particles, especially if they do have some carbon, and the carbon has a surface burning on it, and later on, finally, it becomes ash and then eject out. In this kinds of combustion process, you may try to analyze it based on like these mechanisms. You have a fuel coming out and has air coming from the surrounding. Those in that condition is very similar to that for the gas turbine. The difference is here, the boundary or your combustion chamber, you should consider there is some heat coming out. Okay, those heat will be used for the heating of the water in the boil, or the heat required for the thermal pyrolysis and the burning for the solid materials. Okay, and you can think about those just heat coming out from the flames. You may go through the heat conduction or radiation out. Okay. The combustion mechanism are very similar to the spray to the gasoline to that for the gasoline the gas turbine engine, because for the industrial furnace you need to try to introduce the flow recirculations to enlarge your region for the thermal content to reduce the temperature lower than threshold burning temperature for thermal NOx. Okay, and you can see those kinds of flow recirculations and flow structures. You can figure out it's very similar to the flow field in the gas turbine combustion. Okay. For the next part, I will give you some pictures to let you experience certain examples I illustrate from the lecture notes. For example, the liquid rocket engine a gas turbine engine, and also I will give you some understanding about the diesel engine combustor.